All right. So thank you very much to the organizer for inviting me to this talk. I'm delighted to be here. It's great to have an occasion to talk a little bit about what we do at Libra. And first, I must mention the elephant in the room, which is that my affiliation is Calibra, and you're seeing right here in the middle of the slide the logo for Novi. Calibra yesterday, literally 24 hours ago, changed its name to Novi. So what is Calibra, Novi, Libra, and how do they relate to each other? And how does that relate to Facebook? That was a common question. And Novi is one of the attempts to explain and clarify all of this. We'll go back over this. But today, I would like for this workshop to give you a hint about the work that is being done to verify some of the implementation of Libra and make it work well using mechanized proof, which happens to be just one formalization method. The things we're going to talk about today is what is the Libra blockchain, how does cryptography implementation, and how we've managed to do a few things in the realm of cryptography implementation verification and consensus protocol verification. A little bit about me. So I did have a past life in research with a PhD on formal verification in 2011. And then I left the field entirely and did other software engineering things. I ended up being a software engineer at Novi. And as part of my functions, I picked up a little bit more mechanized proof and formal verification. And that's what I'm going to talk about today. You can find me on Twitter at Reedsecure, and I'll make the slides available the moment this talk is finished. So first, what is Libra? So Libra is a large blockchain project. It's built on a secure, scalable, and reliable blockchain, and it's governed, and it's in technical terms, it's proof of stake, permission for now, PBFT style leader-based partially synchronous consensus. But basically what this means is a blockchain that is governed by an association. The association is here to provide provide many services on this blockchain, among which one member of the association, Novi, ex-Calibra in this case, aims to provide a payment solution. But that's the business case. The technical case looks more like this. Libra is a large-scale open source blockchain project that you can find on GitHub, written mostly in Rust, and that comprises at least 200,000 lines of code of Rust, and a total that is nearing now 300,000 lines of code. Okay, now, what does verification mean in this context? Usually, software verification is we have a piece of software, it's critical, we need to drill down into everything in that software to make sure there are no bugs. Once we're done, there's no bugs, we can send the rocket to the moon. But in the case of Libra, the mission is really to reach a global scale and to provide, yes, a financial infrastructure, but that empowers billions of people. So some projects only ship, sometimes literally, when everything is formalized, and this can't be one of them. There's no guarantee that if the progress of verification can delay releasing the product. And there's far more keyboards and engineers producing code than there are keyboards and engineers committed to verifying it. So the question is, can we provide scalable contributions to a fast-paced project? So let's drill down into what Libra is a bit more to figure out the interesting parts. If we really simplify what a blockchain is, we're looking at a Russian doll. You have cryptographic operations such as signing and verifying, which, as many as the attendants of this conference, are crucial to the PBFT class of consensus protocols, where people propose a block and then people sign on it. And those enable the engineering of one of those consensus algorithms. And those consensus algorithms then allow you to order transactions for which you can then propose a smart contract language and a VM that lets you write interesting programmatic transactions. there's many other parts, but I'm abstracting them away for the purpose of this talk. Now, on this talk, we're going to look at mechanized proof applied through external and internal projects at Novi to both cryptographic implementations to make sure that those libraries contain code that we can rely on and that doesn't contain any bugs, and the consensus algorithm, which is a distributed algorithm that is really deployed on the Libra testnet for now and soon on mainnet. And we want guarantees that those perform as intended by their specification. Now, I'm going to assume some level of familiarity with mechanized proof. Basically, you write mathematical statements and a specification in a programming language that a computer can understand, develop a proof using that domain-specific programming language, and the computer is able to verify the proof in question. And you have a few references on this slide for intro material you can piggyback on to get really quickly more familiar with the subject. All the proofs that I'm going to present today will be using the Coq theorem prover, and one particularity of Coq is it has this extraction mechanism, which means that basically you are able to develop proofs on functions that corresponds to runnable code, and it can elide all the proof material out of your proofs to leave you with just the runnable code, and therefore give you certified code that you can work with. And we'll see how we have fared at Novi with this particular mechanism. This is not by far the only formal verification, efforts, formal or not, in Libra. There's plenty of awesome things that we won't have time to talk about, from using type-directed API design to model checking, and a lot of interesting work has been mentioned publicly in various talks. Is very specific and more advanced variants of fuzzing, including a great paper that gives a white glove approach for doing this for BFT style protocols. This is the slide you want to look at if you're looking to invite speakers for further talks, because all the people mentioned in this slide have interesting things to say about the subject. Okay. So let's look at cryptography implementations. Libra uses as its main workhorse EDSA for signing and verification, which is crucial in consensus, in transactions, and pretty much everywhere we need that functionality provided, as well as X25519 for Diffie-Hellman key exchange and network authentication and network pipe encryption. So the goal here is to ensure that the EDSA implementation corresponds to a well-known specification. And if you are launching such a large project, you want to choose a specification that is really reliable, especially looking at the context that you're building this in Rust, as many blockchain projects do it on a daily basis. And the risk here is that those cryptographic libraries are actually really difficult to write. Now, everybody knows about the Hardly style bug that happened on OpenSSL a few years ago, and we therefore know that relying on open source projects that may contain bugs and that are underfunded is a risk, right? But there's more to this story. If you look at the way a cryptographic library for elliptic curves looks like, it's another Russian doll. So you're building the notion of a field and field arithmetic that must be implemented on your machine, and your machine has efficient representations of those bits of a certain length, 32 bits, 64 bits, architecture on which you build a curve arithmetic. So that's the notion of an algebraic group defined over the field. And then once you have all of this algebra available, you define protocols that use the group operations to do things such as signing and verification, and signature verification. Now, the problem with most implementations that you will see out there is that those are not implemented with any separation in between those layers. So in a signing function, you may end up seeing bit pushing operations that directly manipulate the field representations that are way, way lower down the stack. And the reason for that is essentially performance. People really want their curve cryptography to be really fast because it is very often a bottleneck, especially signing and verification in those very large blockchain projects. And the result of that is bugs. The bugs that you can see listed here concern landmark projects, some of them somewhat familiar for their, infamous for their bugs, such as OpenSSL, but also in ACL implementations of ED25519. If you look at the right column that gives you the cause for the class of bugs, you are looking at, oh, okay, it's really difficult to implement things on a fixed bit length and a machine word length. But if you look a little bit further down the list, you see non-prime P's and points that are not on curve. So you need to validate your inputs. So input validation bugs are an issue as well. And you need to validate them in mathematical terms. You need to check a curve equation to check the point is on curve. And then there's things that are of the range, not just of the word representation or the math, but RFC and specification. So elliptic curves have this point at infinity, and the point at infinity is sometimes represented as the 0-1 tuple of coordinates. Sometimes it's represented as something else. The specifications are kind of fuzzy on this. And you find this as the root cause of other bugs, as well as padding checks. This is barely half the list. I'm just skimming the surface. You'll find it much more on the website of a great MIT project that we're going to talk about called Fiat-crypto. But as to Libra's choice of Rust cryptographic libraries, we're talking about the Dalek suite of libraries that define EDDSA, X25519, Curve 25519 underlying that. All of this in pure native Rust. And this Rust library took the bet of cleanly separating the field arithmetic, the curve arithmetic, and the cryptographic operations on top of them. The advantage is what they're leveraging, though, as their workhorse that allows them to do that is Rust principles of abstraction, higher level abstractions without cost. And the advantage is that the idiosyncrasies of the bit representations don't pollute the higher levels of the protocol. And so you can have a better code reuse, as well as occasionally write the odd pluggable backend that works with super duper fancy new instructions that we have for some processors, such as AVX512 and its latest instantiations IFMA. But those modules are great and they form a sort of compartment, but can we still have bugs inside Rust code? And the answer is yes, of course. So we'd like to use some mechanized implementations to get further assurance that we don't have any bugs. And there's a great MIT project called Fiat-crypto. You'll see the paper reference here that develops proof of functional correctness for a large range of cryptographic operations, including field arithmetic and some curve arithmetic, and they develop it in Coq. The theorem you can see in their library look a little bit like the one I have under there, where we are proving property of the submod function somewhere in there, and showing that if you evaluate what it does, you get what you expect for subtraction modular reduction. Those proofs can then be extracted to really fast C code. So the good part here is, despite me having talked about Coq's extraction mechanism, Fiat-crypto is not using this. The idea is that the Coq extraction functions on representations of basic primitive types and naturals that are not really wieldy for performance. And on top of that, here we really want a very high level of additional control over our implementation. So they have their own syntax embedding using a technique called parametric higher order abstract syntax, but this intermediate representation is the thing that they prove functional correctness on, and then they mechanically derive it in Coq down to C code. And it produces code that can be specialized at the call of some parameters to any machine word size, and that's really important to us, as well as to any curve parameters. And here we have our favorites. The bad thing is that when we picked up this project, it only produced C code. And so it came at some performance cost to use it because the LLVM Rust compiler, when it needs to make to use several successive calls to a C API, has difficulty optimizing throughout an optimization boundary. So through the help of a fantastic intern and PhD student of Andrew Apple named Zoe Paraskivopoulou, we have contributed a Rust code production engine to Fiat-crypto, and then automated a Rust package release. And then so that we could have easier access to any of the good formalized code for field and curve arithmetic that is produced by Fiat-crypto and that we trust. And then we ripped open Dalek and replaced it inside. And everywhere we could replace a Dalek operation by a Fiat-crypto operation, we've done it in nearly 300 lines diff that was of offering our developers the same Rust library without any modifications to the higher level API, but with an underlying architecture that is completely certified and extracted from proof of functional correctness. There is no change to the developers. Their workflow is not impacted. They are not slowed down. And the reason we've been able to do that with a relatively minor investment is that Dalek has a really clean architecture where it's really easy to replace its base operations. That's usually something you can only do in a, Fiat-crypto is a project that is also used by Google in Boring SSL, and it's used by Firefox, but its use is a much less direct approach, and they have a lot more machinery and a lot less robustness in deriving those fast implementations from Fiat-crypto. And a side benefit is that not only can you use this in any Rust project, whether it's Dalek or something else, today, because we have this automated crate release that follows every release of Fiat-crypto, but because we've helped Fiat-crypto have a pipeline that produces code for another language, it now also produces code for Go and Java. And so that's a pretty cool side benefit. Now, as far as performance is concerned, we have benchmarked Fiat-crypto and we've obtained very nice performance results, which are of the class that we want to see, which is that Fiat-crypto is within 5% of Dalek's performance. Dalek is the fastest EDSA implementation that we know. In any language or architecture. This performance this close to the optimal is really, really difficult to obtain because there's a lot of things you can do to be faster than select implementations of ECDSA, but native EDSA is already pretty darn fast. So when you're getting this close to the optimal, it's really encouraging. We know exactly where there's a performance delta, but it's a technical issue. You have to ask me questions after. What about alternatives? So if you look at a recent paper called SOK, Computer-Aided Cryptography, there is an alternative in the room, which is the Everest project, a fantastic project centered on certifying the entire stack on TLS based on based on F star, sorry. And the reason why we didn't go for this is mostly economics of integration. At the time, we were looking at this project, Valid didn't exist, which is the pipeline that allows Everest certified proofs to compile down to really fast assembly. And in our context, we are building Libra not only as a Rust blockchain, but in a multi-platform context. And the idea here is that the Libra blockchain is the backend for an ecosystem. we really want to have all the association members, but also any interested parties to build wallets, exchanges developed on the platform. And if they're able to reuse our cryptographic libraries, that's great. But a modern client these days is no longer a web browser. It is an application on your smartphone that probably runs with an ARM processor and doesn't necessarily care about x86 64 assembly code. We also have partners that run HSMs to manage their keys. Those hardware modules are found on PowerPC architectures, and that's not code that is necessarily easy to produce assembly for. So this highly multi-platform choice is a big challenge, and we can't hinder it for the purpose of verification or get people that work with smartphones to be second-class citizens because they don't get our formalized code. So the nice thing with Fiat-crypto is that we had the opportunity of delivering this. But with that being said, the journey is really 1% down because there's a ton of future work we'd like to see on Fiat-crypto. It doesn't verify all the operations it calls. It could. There regularly are better mathematical methods for implementing efficient curve primitives. The latest is by Thomas Pornin last month. That means the latest I know of. I haven't checked this morning, and I should. We regularly need new curves. New elliptic curves because of different crypto. There's pairing-friendly curves that have become really important for zero-knowledge protocols. There's a Cambrian explosion in a subclass of zero-knowledge protocols called SNARK, and they find interesting and new ways to combine curves. And the nice thing with Fiat-crypto is that this can offer you a bootstrap, an initial bootstrap to the implementation of arithmetic on those curves because they are really parametric in any curve parameter. So you just punch in your parameters, get the code extracted for you, and you get something that's fast and runnable. This is really hard to implement right if you're doing it from scratch, and it's performance critical, especially for zero-knowledge protocol. So we would love to see further work on Fiat-crypto. We're already, we're very enthusiastic about contributing to it. And I'm personally working on extending some operations there. But it has a great potential for making a sub-range of cryptography really, really better in terms of software engineering at a very modest cost and without any slowdowns of innovation. Okay, so that's what we've done for the cryptographic implementations. Let's move on to the consensus protocol. So I briefly mentioned that the consensus protocol was PBFT style, leader-based, permission, proof of stake protocol. Let's unpack a little bit of that jargon. So if we're looking at a PBFT protocol from a very high level view, you have a leader that proposes a block. He's himself one of the validators. You assume that 2/3, but no more, of the validators are honest. And they follow the protocol, and they receive those communications after a maximum delay once things have stabilized. It's a partial synchrony assumption, and you'll have to look into the details to see exactly what that means. Roughly, the answer to this proposal with votes or absence of votes on whether the block should be committed and taken into account. Those votes are tallied according to a very specific protocol that takes into account the stake of the voters, and you will find a link to the textbook for the nomenclature, right? So proposal, some validators are honest, the others can do whatever they want and try to mess up things. Votes come out, you tally the votes, and hopefully you have a commit. What should we prove of this PBFT style protocol? There's essentially two properties that we really care about. One is safety, also known as the no fork properties, meaning that the honest validators agree on the sequence of committed blocks. And liveness, committed blocks are continuously produced. Now, LibraBFT is an extension of the hot stuff family of protocol, which is not named for Donna Summers at all. It's named for a family of by cartoon characters. We've extended the hot stuff protocol that with liveness conditions, and you'll find the references to the two key papers down there. The general idea of LibraBFT and hot stuff and what it brings to the table is this notion of optimistic responsiveness. In any of those PBFT protocols, when validators don't really agree on a proposal, there's something that occurs called a view change, and most protocols reset to where they were at the beginning and restart everything. And basically, Libra resets to a safe, known, acceptable checkpoint for all, which is why I mentioned it's Knuth-Morris price for consensus. You get this optimistic responsiveness because you're a little bit like the Knuth-Morris price algorithm. You reset to a very reasonable place to restart your reflection. I should mention that this workshop is pretty hot stuff heavy because you're going to get another invited talk from Dalia Malki, one of the inventors of the protocol, on June 24th. And on July 15th, you will get one of the other, Itai Abraham, another of the main implementers of the hot stuff chain of the hot stuff family of protocols. And even though his talk is not really on that particular topic, I hope you'll be able to ask questions. Right. So looking at PBFT protocols and mechanized proof, we already have a very long background on PBFT style protocol. The PBFT itself, the paper is 21 years old. And there are some formalization results for this ancestral PBFT protocol specifically. You'll find it in the Velisarius paper for Koch. But there's a lot of work going on and growth and dynamism, including sometimes researchers that disagree on particular finer points and finer properties here, the liveness property for the synchronous hot stuff, a very recent proposal and a very recent claim of a deadlocking attack against this. I have not verified any of this. I'm just saying those are two researchers talking. Tendermint is a very close cousin of this class of protocols that is also used in Cosmos, and the Algorand is also very close. And there's a big gap that is forming now between the PBFT protocols that we know and formalize and the modern PBFT style descendants that have moved away quite a bit from the old PBFT discipline, and for which we don't have a lot of formalization results. So, it would be an interesting research asset to have a way to formalize those modern PBFT style protocols. But I'm not completely entirely a researcher, and I still have to pay attention to the impact on the actual project. That's another thing we were gunning for. Let's say we have a proof for LibraBFT. How do we connect that with the actual Libra code base, right? A certified library helps the protocol development, but can it give us confidence on the code? Now, the consensus module is 15,000 lines of code. And in terms of mechanized proof, there's just me. So I can't review every single line in there. A Fiat-crypto-like approach where we would be managing our own consensus code and then extracting it to runnable code that we run in the LibraBFT platform would be done either with, this extraction would be done either with the native Koch extraction mechanism, and there's references from Pierre-Lias' master's thesis on there that show that the performance is absolutely prohibitive. And the other alternative would be to have our own syntax embedding, and that's not a work for just me, and I'm working part-time on this. But there's a distributed protocol that gives us an opportunity for having a link between the proof and the actual code base. So let's say we have a safety proof. The no-fork property, validators vote on block proposals. They do that in successive rounds. The safety property is that the votes, if we have those BFT assumptions, cannot lead to any forks. And they translate to invariance. They say, if the honest validators follow the protocol, then we have this global invariant on the distributed systems. Two valid blocks are considered committed if they are in the same chain. Global hypotheses follow from the local invariants. Turns out those local invariants, known in Libra as the safety rules, are relatively simple arithmetic inequalities on integer counters. We also have developed throughout Facebook and Novi the Mirai abstract interpreter for Rust that performs abstract interpretation verifications on Rust code. And those Mirai annotations are sufficient to maintain local invariance throughout the validator code. So if you have a proof that connects really well to those local invariants, you can check that the local small invariants exist in the code, and the proof is the guarantee that those small local invariants entail the global invariants. We've written a lot of definitions to get to that result. It takes a lot of work to define a modern PBFT protocol, especially considering the state of the existing literature and COG code bases. So we've completed a complete safety proof and all the definitions that are necessary for it, but we're still working on liveness. To do that, we've used every trick in the book to be able to do this in a minimum amount of time, because again, it's just me and I have other responsibilities as well. So we've used SSReflect, a specific proof language for an alternative proof language for COG, as well as the SSReflect libraries that allow you to operate in a finite gives you a lot of speed up if you're operating in a finite domain. It's an approach that has been taken by Ilya Sergeyev's work on ToyChain, and to the best of our abilities, we've tried to extend this work. We have very few axioms and hypotheses beyond the BFT protocol. There's a definition of honesty in there that does a lot of work on these slides, but we have completely standard axioms on hash functions, injectivity, and we basically state that we can sign things and verify signatures. And it was really easy to notice that blockchains operate on a finite domain, because at any given time, especially considering if your blockchain is permissioned, you have a finite list of distinct validators, and you have a finite number of blocks that have been seen by anybody at any given time that could be considered to be committed or not. And therefore, we get all this nice speedups from the SSReflect libraries. And we get a final theorem that if you've read a paper on the hot stuff consensus, is relatively readable. And we've circulated that around to get external confirmation from people that are not me, to understand that, yeah, that's the safety protocol of hot stuff. So basically, hot stuff creates those tree chains, which you can see with the path statement here. And basically what they say is, if you have two tree chains, either one follows the other or the other follows the one. That's your safety no-fork property. The final tally, to give you a sense of the size of this proof, is that this is under 2,000 lines. This is around 2,700 lines of code. It was about 3 François months, spread over about 6 months in real time, because again, that was not my only responsibility. And the last call that I can take as a takeaway from this experience is that it's great. I've managed to complete at least the safety part, and I had not touched formalization or COG or SSReflect for close to 10 years, 8 years actually, since my PhD, like not touched at all. So picking up things shows that COG is a mature tool, SSReflect is not mature, but first, there's room for so much more than just smart contract verification. Don't get me wrong, smart contract verification is great. We do a lot of it at Novi. We're not at Mechanized Proof yet, but if you want to work with us on that, we're hiring, talk to me after. But there's many protocols that could benefit from consensus formalization. It has a consequence in code, meaning that you reduce the big complex global invariance of a distributed protocol to small local invariants that you can actually reasonably verify in your implementation. But the problem is productivity, right? I have a ton of responsibilities besides this, and I can't devote my entire time there. As well as much as that, teaching is extremely important as well. Proof engineers are a rare breed. I was lucky to have an internal code reviewer, Vincent Siles, because I have an employer that is a large software company that has many employees, and they had hired this guy that I share 2 PhD committee members with. But that's not a scalable solution for getting proof and mechanized proof as a practice in industry. And there's also some effort to make SSReflect a bit more. So to reinforce my point, in case you found this talk really, really bad, I'm linking here to a much, much, much better, greater talk, which is a high-level view with data of how the demands on software engineers look like, and they're not lessening anytime soon. I was really lucky and fortunate to have time to spend working on COG as part of my duties, but I'm conscious that this is an extremely privileged position. And for mechanized proof to have this sort of impact on a real software project, every little gain of productivity makes mechanized proof easier. That includes prof libraries, tooling. I know people working on tooling on the research side often see it as a very ungrateful job. I'm here to tell you, thank you. I could not have done it without you. And not without the whole host of contributions to my work, ranging from consensus researchers, cryptography researchers, the Mirai authors, and the external library authors that have written, that are really the giants whose shoulder I'm standing on here today. Thank you very much.
Thank you, François. I don't know how we perform the big applause. I know we have this feature, but in any case, let me do it for the rest of the people. Such an inspiring talk. I don't know if we have questions. We're kind of running out of time, but as we may take maybe a quick question from, okay, Connor.
Hey, no, it looks like there's no questions in any of the chats, so I think everyone just really liked the talk. So thanks, François.
Thank you very much. My pleasure. And again, if you have a special interest in mechanized proof and you want to drill down on the details of this talk or ask me pointy-haired questions on some tiny details, don't hesitate to do so. I will be hanging out in the Zolib chat after the talk.
Great. Thank you again.